Right, so this is some joint work with Simona Lintz that actually came out of nowhere. We weren't actually trying for this problem at all. It was completely unexpected, trying to do something else that we couldn't do. But anyway, so here's something that was worked last year and it's just been published. So here's a well-known result that many of you will know. It's probably the first result you learn if you're doing mathematical phylogenetics. And so what you've got is you've got a set of rooted triples, and just as a reminder what they are, so there's rooted triple, it's just a subtree on three rooted binary phylogenetic tree on 3 leaves. And if you take all the set of rooted triples displayed by some phylogenetic tree and it's binary, it's required, then up to isomorphism, T is the unique tree whose set of displayed rooted triples is R. Okay, so those who don't know displayed, I'll give that definition shortly, but basically it's inferred. Those triples are inferred by that tree. All right, and the other thing is you like to know is that T can also be reconstructed in polynomial time from R. All right, so that's one of my first results you see, and it's certainly one of the first results I saw when I was doing phylogenetics many years ago when I first looked at phylogenetics and worked in the area. Why do you care about the theorem? You might care about the theorem because actually it underlies any supertree method. Well, any might be a bit strong, but typically most supertree methods will have this underlying theorem. All right, so a supertree method, you take the input is a collection of small trees and you want to combine them into a single tree that best represents the initial collection, whatever best may mean, want to best represent. But if the collection is consistent, i.e. you can come from a single phylogenetic tree, then you'd like to be able to construct that tree. All right, and that's where that theorem comes in. The classic supertree method is the build algorithm from 1981. Actually, they were doing databases, I think, from memory in the paper, nothing to do with phylogenetics at all, but the algorithm just applies straight away. All right, and for their algorithm, I'm going to come across that at the very end, the build algorithm. It takes a collection of rooted triples and decides whether the rooted triples are consistent, i.e. comes from a single tree, can be displayed by a single tree. So what we would like in the world of doing phylogenetic networks, we'd like to have the same approach. Can we take a collection of trees and find a network that's consistent with those trees? All right, so we're asking for analogues of Theorem 1 for phylogenetic networks. Now I can always find, you give me any collection of trees, I'll always find you a phylogenetic network that is consistent with them. That's no problem at all. But here we're going to want the uniqueness as well. There's only one phylogenetic tree, which those set of trees are displayed. Okay, so that's the overall problem we're looking at. Right, so just as a, I don't know, warm up, but many of you know, looking across the audience today. So what's a phylogenetic network? Well, all ones we're going to be interested in are rooted in binary. Okay, so they have a root about degree 2. What else do they have? I'll quickly just draw this. Where am I missing one? Oh, I was missing one for my picture, doesn't matter. I don't know, hopefully that's okay. So there's a phylogenetic network there on 5 leaves. So these are the leaves down here. So they are the leaves. We have tree vertices, and they are the vertices of in degree 1 and out degree 2. All right, and they correspond to speciation events, if you like. And we have reticulations and they correspond to vertices of in degree 2 and out degree 1. All right, and they correspond to reticulation events, as the name suggests, something like hybridization, or it could be recombination, and those types of things. All right, so that's what a phylogenetic network is. If I didn't have any reticulations, then I have a rooted binary phylogenetic tree. Okay, so that's the little last line on that slide there. And from now on, we're going to drop rooted and binary. And often if I say a network, I mean a phylogenetic network. I will keep saying a phylogenetic tree. There was a reason for that. I can't remember, but there is a reason for keep saying phylogenetic tree somewhere in the talk. So I'll keep saying that. But if I say a network, it just means a phylogenetic network. But I'm going to drop rooted and binary. Because all throughout the talk, they're all rooted and they're all binary. Right, so we're going to come to the notion of displaying. So you can think of sometimes you can actually think of the network as actually being an amalgamation of gene trees, and they just happen to conflict, and that's why you have reticulation vertices. And so you want a notion of displaying. What does it mean for a gene tree to be inferred by a network? So a network again displays a phylogenetic tree if it can be attained by repeatedly deleting arcs and vertices and suppressing vertices of in degree 1 and out degree 1. Another way of saying that is I can embed the tree in the network. So for example, if I took, no, I should have done it at the beginning. There you go. Oh, skills is teaching online classes. So if I take my network there, here's a tree I can embed in that network. Let's see. So there's a tree I can embed in the network, and I could look at B, C, D, and E. All right, and there's the orange embedding. And if I was to delete vertices and edges that are not used by the embedder, and then suppress any vertices of in degree 1 and out degree 1, I get the displayed tree on the right-hand side. All right, so that's what we mean by the notion of displaying. And there's that theorem, the original theorem we had. If R is a set of triples displayed by a phylogenetic tree, I've drop rooted. Then T is the unique phylogenetic tree whose set of triples is R. All right, and I've also dropping isomorphism, but everything's up to isomorphism. Okay, so T is the unique tree whose set of triples is R. So if I take some tree, all right, so I've got some tree A, B, C, D, E, F, and I take all the rooted triples of that tree. All right, then for those set of rooted triples, there's exactly one tree for which they came from. That's precisely the set of triples of the tree. Okay, precisely the set of triples of the tree. And in this case here, it's that one there. So that's what theorem 1 is saying. All right, and what we like to do is get network analogues of that result. The input of trees each time, and I want to find a network for which they are precisely the trees displayed by the network. So the natural examples you go to if you want to try and generalize the result for trees is a level 1 network. And so a level 1 network's one where it has the underlying cycles are vertex disjoint. All right, so if I've ignored the direction of the edges and I look at the underlying cycles, they are vertex disjoint. All right, so for example, this one here is not level 1. Here's 2 cycles here. All right, here's one, and there's another one, and they're not vertex disjoint. All right. So here's a result of Philippe Gambert and Katharina Huber that says if R is the set of triples displayed by a level 1 network, then N is the unique level 1 network whose set of triples is R. So that looks like it generalizes it straight away, but there is a proviso. Each underlying cycle has to have at least 5 vertices. And the reason for that is this. So there's level 1 network. It's got one underlying cycle. Have I got this right? Someone will tell me if I haven't got it right. Oh, that's supposed to be C, isn't it? All right, and both those two networks display these two triples. All right, ABC and BCA. The one in this one here, and the second one, you might like to know that the root of triple doesn't necessarily have to coincide with the root of the network, but there's BCA line there. And if you want to see the other one in the second one, I go BC and then A, and there's the two trees. Okay, the one on the left is a bit more explanatory. So they're both level 1 networks, but they both have underlying cycles of size 4. All right, and the thing that mucks that up is, and what marks many things up in this world, are shortcuts. And that edge there is an example of a shortcut. All right, so what's a shortcut? It's a reticulation arc. So let's see, probably too many colors here. Let's reduce some of the colors. Oops. So it's a reticulation arc where if I look at the other end, that's its partner, so the reticulation arc going to the same vertex, this one here is an ancestor of the other one. All right, and that creates this. So if you think of you coming down the page, I should have said that all arcs are directed down the page. If I'm coming down from the root and I hit this vertex, there's a shortcut to this reticulation going via this way. So that's a shortcut. All right? And those shortcuts give a little bit of grief in this world. But trying to capture them is difficult, basically. It's difficult. So what if you generalize level 1 networks, but we're not going to allow shortcuts? So a network is normal if every non-leaf vertex is the parent of a tree vertex or a leaf, and it has no shortcuts. So here's an example. So there's a normal network. And if I was to pick any non-leaf vertex, it always has a child, or it's always the parent of, either a tree vertex or a leaf. So in this case, it's a parent of a reticulation, but it's also a parent of a tree vertex. All right. And every interior vertice, non-leaf vertex, has that property. All right. So that's network said to be normal, and it has no shortcuts. Okay. So here's a result for normal networks. And this is Stephen Wilson in 2011. And if T is the set of, I'm using T for a set here. If T is the set of foliage in X trees displayed by a normal network N on X, then N is the unique normal network whose set of displayed trees is T. But notice here in Stephen's theorem is that it requires the trees that have the same leaf set as the network. Right, and so because normal networks, if it's got k reticulations, has 2 to the k trees, then that means it's the number of trees I need to determine or to give me the uniqueness result grows with the size of n. Right, grows with the size of n. Unlike, for example, Philippe's and Caddy's theorem, which it doesn't grow with the size of n because you're just looking at triples, trees on 3 leaves. Okay, induced trees on 3 leaves. So in some sense, we're going to do something for normal networks, but we don't like the idea that you're using all the trees have the same leaf set as the original, as the network itself. So phylogenetic trees are caterpillar. There's exactly one cherry. I've got a definition inside a definition. It's not particularly good, but here's what I mean by that. So a cherry is a pair of leaves with a common parent. So X1 and X2 is a cherry. It has a common parent. All right, so that's a sample of a cherry. And a caterpillar is a tree that only has exactly one cherry. So this is an example of a caterpillar. Whoops. All right, there's an example of a caterpillar. A tree with exactly one cherry. So I don't think I won't explain that. Didn't need to explain that anymore. Another way to define caterpillars, there's a path from the root to a leaf that has all the that passes through all the non-leaf vertices. Okay, there's another characterization of a caterpillar. So a quad is a four-leaf caterpillar. I'm going to call that a quad. And a three-leaf caterpillar is what we've seen before, is a triple. So they're four-leaf caterpillars and three-leaf caterpillars. And what the main theorem of the talk, in fact, the only theorem of the talk and some new theorem of the talk is this one. It says that if R and Q are the sets of triples and quads displayed by a normal network, so I take all the triples and quads displayed by a normal network, then those triples and quads are enough to determine the normal network. It's the unique one with that set of triples and quads. Okay, it's the unique one with that set of triples and quads. That's the first part of the theorem, the uniqueness result. You can reconstruct from R and Q. I don't know, the running time somewhat arbitrary other than its polynomial time. It is in the size of X, but that's simply because a normal network, the total number of vertices is linear in the size of its leaf set. Okay, is linear in size of the leaf set. So you can put the running times in terms of just the size of the leaf set itself. All right, but the point is I only need the triples and I only need the quads. Okay, I don't even need the other four-leaf phylogenetic tree. All right, we don't need trees looking like this, which is the other type of four-leaf tree. We don't need those ones at all. All you need are the caterpillars on four leaves and the caterpillars on three leaves. Okay, so two questions. Here's two questions. We're going to see how, roughly give an outline how the proof goes shortly, but here I just want to look at two questions that you may be thinking about. Are normal networks determined by the set of displayed triples? And the answer is no. Remember, normal networks have no shortcuts, so there's reason to believe that that could be true. But there are two normal networks there, N and M1. All right, and they display exactly the same set of rooted triples. All right. So if I look at the rooted triples for this one, it's R. It's also the same for that one over there, and they're not isomorphic. All right. Just by the way, just for those who I should have said at the beginning, when you talk about isomorphism for phylogenetic networks or phylogenetic trees, you have to map vertices to vertices in a way that preserves the relationships between them. But yeah, in this case, A has to be mapped to A, B has to be mapped to B. So the mapping is an identity on the leaf set. Okay, that's what you mean by isomorphism. So that's okay. So that's not true. Not in general. Whoops. So no, not in general. So we do need the quads. For those who are familiar with normal networks, there's a slight generalization of normal networks called tree child, which has the property that every non-leaf vertex is the parent of a tree vertex or a leaf, but you allow shortcuts. But this time you're going to allow shortcuts. And you say, well, so the class of tree child networks contains the class of normal. All right. And I should also say that tree child networks, I know Leo and Crowd, I can't see Leo, I only got so many faces I can see at the moment. They often like their level K networks as their first choice. My first choice for networks if we're looking at a problem is tree child networks. Don't know, that's just what it is, but that's what I do. And you ask the question, are tree child networks determined by their sets of triples and quads? And the answer is no, they're also not. And I haven't left enough space on the page here, but let's see what I can do. So I can go back to my two level 1 networks. They're tree child. All right, level 1 networks are always tree child. Okay, so there's the two you've seen before. I'll give you a third one that's not level 1. If you can see it through the writing. That is a tree, that is a tree child network. They display the same set of triples. There's only 2 they each display, despite the complication of the right-hand one. It only displays 2 rooted triples. And then what I could do is say, well, okay then, but that's got no quads. Yeah, sure, because I only got 3 leaves. Well, let's extend that. We're adding a caterpillar-like structure. Onto both, all 3. All right, but the ordering on the leaves is the same. And those 3 trees there, I can make them arbitrary size, and they have the same sets of triples and quads. All right. They're the same sets. Oh, sorry. I'm gonna. Is that right? Yes, I'm okay there. I was just having a little panic attack because actually the 2 left-hand guys, oh no, that's right. No, I'm fine. Sorry. I'll take that all back. I was having a little panic moment then. So those 3 trees there, they have the same triples and quads. In fact, they have the same trees. All right. So remember, Stephen Wilson's theorem says, if I'm a normal network on X, and I take all the set of phylogenetic trees, phylogenetic X trees displayed by the normal network, and that's precisely the unique normal network with those display set of trees. It doesn't hold for tree child. All right. All the trees displayed by those 3, the tree with the same label set as those 3 trees there, they have the same set of trees, and there's 3 different networks for them. So that's certainly not true. All right. So in some sense, normal's at the sharp end of this result for quads and triples. Don't know. Maybe that's not so precise. Right. So what I'd like to do for most of the remainder of the talk is just to give a little bit of a flavour about how do you go about proving such a result. So the first thing is you've got to latch on to it's proof by induction, and so you've got to latch on to something that you can reduce the normal network by and have some control over. So we're going to do that because normal networks have certain structures. They always have a cherry or a reticulated cherry. So cherry we've seen before And I'm using P of A and P of B to denote the parent of A and the parent of B. So there's a cherry in a phylogenetic network, simply a pair of leaves with the same parent. That's the cherry. Its counterpart is a reticulated cherry. And that's a pair of leaves where PB is a reticulation. So the parent of B is a reticulation. And we also additionally have this arc, PA-PB. All right, which necessarily means that P of A is a tree vertex. And that's a reticulated cherry. And as many of you know, if you're working on a lot of these sort of types of networks, if you've got a cherry and a reticulated cherry, they make a very natural object to do the reduction on. Right, so here's a little result that we need. If n is normal, then n has either a cherry or a reticulated cherry. And in fact, that's actually not that hard to prove. Start at the root, take a maximal length pass to a tree vertex from the root, or a maximum, it doesn't matter. I'll say maximal, but maximum's also good. Take a maximum length path from the root to a tree vertex. All right, let's call that U. Then since it's normal, it's either got a tree vertex or a leaf as a child. Well, it can't be a tree vertex because that was supposed to be a maximal length path from the root. So one of the children must be a leaf. Look at the other vertex. It can't be a tree vertex, otherwise it's not a maximal length path. So it could be a leaf, which makes that a cherry, or it could be a reticulation, but below that reticulation can't be a tree vertex, would have to be below that reticulation is either a tree vertex or a leaf because it's normal. It can't be a tree vertex, otherwise we could have extended the path, so it must be a leaf. Right, so actually that's quite straightforward to see. So normal networks have that property. And what we'd like to do for the reduction is, for many of you that'll be familiar, a natural choice is to, if you've got a cherry, is to simply delete B and suppress that degree 2 vertex. That's a normal network. And in the case of a reticulated cherry, the natural thing is to delete that reticulation edge, PA, PB, and the resulting thing is also normal. But in this case, we're not going to do that. For the cherry, we'll keep the same move, but for the reticulated cherry, let's call that GB. I don't know what's down there. I don't know what's above that part. And what we're going to do here is we're going to delete B. We're also going to delete PB, the parent, and then suppress those two degree 2 vertices. All right, so we'll suppress GB and we'll also suppress PA. So it's slightly different than the usual approach. I think the proof would work going the other way, but it's different, and I'll explain where the difference and where the there's a complicated process in whichever direction you go in, you're going to hit something that requires some work, and so I'll show you where the two differences will arise when we get to it. Right, so that's how. So we're going to do induction in that way. Thing is, I need to be able to have the quads and the cherries. Sorry, the quads and the triples being able to recognize cherries and reticulated cherries. So we've got to have the fact that the triples and the quads can recognize cherries and reticulated cherries for this to work. Because remember, that's the input. All I'm given is a set of triples and quads, effectively, and then I've got to try and show I can recover n. is what I'm really trying to do. So, oh, I know I was going to do not that first. So how can I recognize if I'm given a normal network, but I've got a normal network, I can't see it, but I've got the triples and quads. How do I recognize cherries? So this is a cherry in a normal network. And if I was taking any rooted triple, X, Y, Z, and I said that A and B was a subset of X, Y, Z, what can you tell me about A and B? And X, Y, Z is a triple of this normal network. Don't look at me blank face. Someone's got to have an answer. Someone? Oh, it's like teaching my class, my second year class. I get as many responses. So I'll do it again. So AB is a cherry in the normal network. And I tell you, here's a triple from the normal network. X, Y, Z. And A, B are two of those leaves. What must A and B be?
X and Y?
X, Y, right, excellent. All right, so thanks, Mark. So there's a character, right? So that's one direction, but that's also sufficient. All right, having that property is sufficient to tell me AB is a cherry. Okay, so AB is a cherry of N if and only if, I'll put that in blue because the notation just means this. If and only if that, whenever I get that triple and AB are two of those leaves, then AB must be XY. Now that's not a surprise, all right? There's nothing deep going on there. That's not a surprise. It's being able to recognize reticulated cherries where a lot of the work comes in. I need a characterization that tells me if I've got the collection of triples and quads of the normal network, how do I recognize reticulated cherries? Okay, so that's more complicated, and that involves, and I need Q this time as well. I need the quads. The other ones I only require the triples. I need the quads. But more than that, I also want to recognize when I do this, the visibility set of G of B. So remember, I'm working in a normal network, so I have no shortcuts. So schematically, my normal network looks like that. The boxes, the square boxes, I mean, I've got no idea what's in there at all. All right, I know nothing about that there at all. But if AB is reticulated cherry, locally it looks like that. And G of B will stand for the grandparent of B, if you like. That's not PA. All right, that's where the G comes from. So what's the visibility set of G of B? They're all the leaves L for which every path from the root to L traverses GB, passes through GB. Okay, that's the visibility set. Because we're normal, the visibility set of any vertex is always non-empty. All right, there's always at least one. And so the visibility set of GB is there's at least one of them. And hang on, Luke. All right, my daughter's about to, it used to be my daughter, I take my daughter to school. Now she drives me to school trying to practice driving. It's scary, I tell you. So anyway, so there's the leaf L. So there's always at least one. All right, there's always at least one. Yep. So not only to be able to recognize using triples and quads for a reticulated cherry, we also want to know the visibility set of GB, and I'll explain why we need that at the end. Okay. I should ask, what sort of things can you get something I was going to do here at this point. So for example, if I had, what sort of conditions might you have here? If the visibility set of GB contained also L prime, all right, then I couldn't have a triple of this form. BL versus L prime. All right, because why is that? Well, L and B have to go through here because the only routes to the leaf go via GB, and they are always going to meet together before B. All right. B can either go this way, going up towards the root, or B can go this way. But whichever way it goes, it is these L and L prime are going to meet before it meets B. So you can't have that in your set of rooted triples. And that's one of the conditions about the visibility set. If you want a quad one, here's a quad condition that you have. I can't have a quad of this form, where L is in the visibility set of GB. I can't get a quad of that form. All right. Where X is some leaf, it's not B or A. So B meets L, then it meets A, going up this way, but X has met B beforehand. There's no way that could happen. All right. B either is going to meet A first, or it's going to meet L first. Mark's looking at it, but you might like to think a little bit more about that, but I can't get a quad of that sort. So my set Q can't contain any quads looking like that. All right. So there's a bunch of conditions, necessary conditions, and then you have to establish they are sufficient, and we can do that. Okay, so we can get a bunch of necessary and sufficient conditions on the triples and quads to recognize reticulated cherry AB, and to also pick up the visibility set. Okay, to also pick up the visibility set. So suppose AB is a cherry, or AB is a reticulated cherry of N. Then, I'll go back one. And then suppose I delete B, depending on whether it's a cherry or a reticulated cherry. So this is N. And I've got one of these two. And I was to delete B to get N1. I was to delete N delete B. How do I find the triples and quads of N delete B? Well, I simply throw out any triple that contains B as a leaf, and any quad that contains B as a leaf, and I'm done. All right. Now, that's the reason for deleting B. Right. That makes that bit much easier. Makes being able to tell me what the triples and quads of N delete B are is because that's much more straightforward. The difficulty with this route and using this induction on deleting B comes at the end when I've got to try and find where I can reattach B into the network. All right, so that's the compromise. It makes it more difficult at the end. So that's what that last line, that's what that last sentence there says. If N prime is the normal network obtained from N by deleting B, then the sets of triples and quads of that network is obtained by simply deleting those triples and quads that contain B as a leaf. Okay. Right, so let's see how we can put all this together. So the proof's by induction on the size of X, the size of the leaf set. If the cardinality of X is 1 or 2, that's not a problem, because either you get a single vertex, or if it's 2 leaves, it has to be that. There is no choice. So now suppose at the size of X at least 3, and you've got at most size of X, and it holds for all normal networks with the most one less leaf. Cardinality of X minus 1. Right, now take a normal network. We see to display triples and quads R, R, and Q. So you've got N. That's where R and Q came from to start with. But now I've got an M1. You see the triples and quads are R and Q. We need to show that N and M1 are the same, are isomorphic. Right, so let's suppose, first of all, that N has a cherry AB. Okay, so I've either got a cherry or a reticulated cherry. You can imagine the cherry case is going to be way easier than the reticulated cherry. Suppose AB is a cherry. Then AB is also a cherry of N1. Why is that? Because N1's got the same set of triples. And we can use the triples. Triples will tell me the cherries of the network, of the normal network. So AB must be a cherry of N1. If you like, just for a little pause, here's A and B. Here's N1. Both of AB is a cherry. So what do? I delete B in both. And if I delete B in both, then by induction they're isomorphic. I've now got one less leaf. And the only thing I have to worry about is I take N delete B and N1 delete B. Where do I put B back? Well, AB was a cherry in N and a cherry in N1, and there's only one place to do it. Okay, so anyway, that is the proof. That's the last two lines of that proof there. Exactly that. Okay. Right, the reticulated cherry part's the tricky bit. Suppose now that AB is a reticulated cherry of N and VB is the visibility set of GB. So here's N. If I look at N1, let's call the parent of A there P1A, P1B. Because N1 has the same triples and quads, it also has a reticulated cherry AB. Where the grandparent, I know the visibility set of the grandparent of B. So if I put the visibility set in here, here's VB, it's the visibility set of GB. And the visibility set of G1B is exactly the same. All right, because I've used the triples and quads for that. Right, now what do? You delete B from both. Well, since N and N1 have the same triples and quads, N delete B and N1 delete B also have the same triples and quads once you remove B. So they must be isomorphic. All right. So N delete B looks like this. N1 delete B looks like this. All right. And now I've got to reattach B. Now I know it's a reticulated cherry in both, so I need somehow to find B. I should have different color. Right, and PB is a parent of B. Now I've got to try and reattach them. Reattaching one of the arcs is easy. All right. That arc's straightforward. Attach. The trouble is the attachment point of the right-hand side. Where am I going to put GB, PB in the left-hand one and G1, B in the right-hand one? All right, and that's the tricky bit. All right, so the downside of deleting B, our operation of deleting B, comes here. If we didn't have to delete B and we just deleted the reticulation arc PA, PB, then it would be easy. But the difficulty would be finding the triples and quads of the reduced tree, of the reduced networks. Okay, so that's where the trick lies, but you can find that. And so that's not problematic. So this is just what I've just said. AB is reticulated cherry of N1, B's visibility set of the grandparent of B. These are isomorphic when I delete B, the same triples and quads. Exactly one place to attach PA and PB. So that's fine. But there's a bit of work to find whereabouts to attach the where attach this and this bit. All right, where to attach that edge, and there's a little bit of work involved in finding that. Okay, I won't talk any more about that, but there's a little bit of work, and happy to, if someone send me an email and they're interested, I can quickly explain that later on. As it's inductive the proof, that gives you rise to an algorithm. All right. Part of that algorithm is also being able to find the visibility set. There's a little requirement there, but you can do that quickly enough. And so that gives you the associated algorithm as well. And I'll just finish on one last slide. As a way as an open problem, if you think about build that takes in as input a set of triples, decides if there's a tree that displays that set of triples. There are analogous algorithms of level 1 networks. Leo and Stephen have got one where they want to do it, but they actually want to minimize the number of reticulations. Some of this work actually started with Janssen and his colleagues in 2006. They were using dense triples to do it though, and I think Leo would tell me, but you require dense triples to do this, which means that for every 3 leaves, I have a triple on those 3 leaves. All right. If they're not dense, I think the problem's hard.
Yeah, exactly. Yeah.
Okay. But of course, the natural question is there something analogous to build for normal networks with when you've got a set of triples and quads? So I'll finish there. Yep, that's it.